Okay, welcome back, everybody. Wow, everybody, the three of you. All right, well, let me share something here with you to give you an idea of where we're at. Hopefully, if you looked at it on the Canvas Court website, but this is their schedule, what we got left over. We have one chapter, chapter 15, which is what I'm going to complete today. Today's the 29th. This coming Thursday, you guys are in red here. We'll have a study day. Again, opened up for any questions, unless I don't finish chapter 15 today, which I suspect I will. It's fairly short. I will, if I don't complete it today, I will continue it and finish it up on Thursday, and then continue with the study day. So that means that next Tuesday, which is on the 6th, you have exam number 5. Okay, so don't forget about that one. And then that is going to be an open study day too, along with the 8th. Okay, so basically we're going to have 3 open study days. And then on the 13th, that's the end of the semester, and that is our final. Our final, like the other exams, are all online. Okay. I also have a course evaluation, course and instructor evaluation that is open now, but I don't see the results until next semester, but I made it a 5-point extra credit. Basically, go in there, search for my name. It's a drop down list. Select my name, select your section, which I wrote there in the assignment. It's like an assignment, but it has 0 points on it. And that's because it's extra credit. And so answer the questions, appreciate any positive feedback. I don't know what the future is with respect to online. I know we're having some next semester that are hybrid. So I know I'll be teaching the lecture, at least at one of my schools, I'll be teaching the lecture online, but the lab will be on campus. And at GCC, we're also doing that. So I'm going to be on campus next semester. So after 3 years going on, doing online work, to almost 3 years, we're slowly taking it away. But I really suspect, and that's, for those of you who like the online, please put that information, because I suspect that online classes do give you a little latitude. Sometimes you can't make it to the campus, obviously. It does give you a little latitude. So if you think you would like at least the chemistry department to continue online, please make that comment in there. We appreciate it. So anyway, so everything shuts down on the 13th. So if you've not completed any exams, now let me reemphasize, the only drops we have is homework and activities. They will drop the lowest one in each group. The exams are not dropped. And so all of them count. Now, I do have the okay to, if you missed an exam, to take your final exam score and substitute that for the missed exam. Okay, so I can do that for one exam. Now, if you feel that for whatever reason you don't want to take, you want to withdraw, and that's okay. Let me know. I could submit a withdrawal, but I can't submit a withdrawal if you take the final exam. So hopefully you're not at that point that you think you need to drop, but I don't think you guys are. No. So let me see what else. Any questions before I finish this up? No. Okay. So let us continue with the final. And we are going to talk about coffee, which is basically what a solution is. Okay. Coffee is definitely any basically any drink other than pure water is a solution. And so we're going to talk about solutions. Oh, there it is. I wonder why I wasn't moving. All right, so what is a solution? So by definition, we have two things. We have a solvent and a solute. The solute is the chemical that is present in smaller quantity, okay? And the solvent is the chemical that is present in the larger amount. Now, we use the term solvent, and we tend to think of it as an aqueous system or a liquid, but we're going to learn that you can have a solution that has nothing to do with liquids. But in general, we look at a solute and a solvent. One of the most common solvents, obviously, is water, but there are a lot of other solvents that are non-water based. They're non-polar, okay, and will dissolve non-polar material. So that's one big takeaway from this chapter, and that is like dissolves like, meaning that when you have a polar solvent and a polar solute, they will dissolve much more readily than if you have a nonpolar versus apolar, okay? Because we know that classic example, I use it throughout the semester, is Italian dressing. Okay, we have two layers. We have an oil layer and an aqueous layer. They don't mix. We've got different polarities. All right, so solute is whatever is present in the smaller amount, and solvent is the chemical that is present in the larger amount. Now, concentration is a function of the amount of solute you have per given solution, per given solvent. You can see here from this, look like glasses of Kool-Aid. Obviously, on the far left, it's the same material, but it's not as concentrated as that container, that glass on the far right, okay? And so it's very dilute on the left, far left, whereas very concentrated on the far right. Now, with respect to solute, there is a limit. Everything has a limit as to how much I can put in how much solute I can put in solvent. Obviously, if you take a gallon of water and you take a teaspoon of, say, salt, table salt, sodium chloride, and you dump it in a gallon of water, it's going to dissolve, right? So the quantity of solvent is quite a bit. But if I were to take like 2 pounds of sodium chloride, it's going to be tough to dissolve it in 1 gallon of water. So you see, there's a certain ratio there, a certain amount of solute that I can put into a solvent. Now, there are different examples of solutions. For example, it is feasible to have a gas in a liquid. Classic example is a carbonated drink, soda pop. Okay, you get soda, you get carbon dioxide, and you blow it into water, and you carbonate. It gets a little fizz in it. It gets a little bit of acidity. I'm sure you can. I know there are these carbonation systems. They got little cartridges of CO2 that you can buy this machine there at Walmart that you can make your own carbonated drinks. And just carbon dioxide being flowing through the solution. You can do the same thing by blowing it with a straw and carbonate your drink because you are exhaling. Excuse me. Excuse me, sorry. You are exhaling carbon dioxide, but obviously it's going to take a lot of blowing with a straw to get it as carbonated as a sodium, as a salt drink. Okay, another example of a solution is a liquid in a liquid. Now, when this occurs is, again, we're going to think of polarity. So normally we're talking about polar dissolvent and polar, non-polar dissolvent and non-polar. A good example would be a drink like vodka and tonic, okay? Then we have an example where you get a solid in a liquid. And that's the example I used earlier. Excuse me 1 second. Okay, I'm back. So sodium chloride in water, you make a salt solution. Okay, the solute is the solid, sodium chloride, and the liquid obviously is the water. Okay, you could have a gas and gas solution. Classic example is the air around us. We have a big mixture of nitrogen, oxygen, carbon dioxide, and all kinds of other gases all around us. Okay. And then you can also have a solution that is consists of nothing but solids, solid and a solid. Steel is a good example. Steel, 100% steel is not a very good metal to build buildings because it's very soft. So what is done is amounts of carbon are put into the steel and some other trace materials. And what that does is it makes a solution, okay? And that solution is, the result is a very strong component. Another example would be brass. Brass is a mixture of copper and zinc, okay? All right, so we can have a solid component. So as I stated earlier, when we think of liquids, like dissolves like. So polar solutes dissolve in polar solvents. It's very difficult to get polar material to dissolve in nonpolar solvents. Okay, so like dissolves like, and the counter of that is nonpolar solutes will dissolve in nonpolar solvents. So we know this example when we have an oil spill, that oil is very nonpolar, made up of hydrocarbons. Hydrocarbons are nonpolar. Water, on the other hand, is extremely polar. The result is the two will not mix. We have a big mix as we show here. Now, when we talk about solids and liquids, we use the term soluble and insoluble. But when we talk about liquids and liquids, the term is not soluble, but it's miscible. When two liquids mix together, we call it miscible. And when two liquids do not mix, it is called immiscible. Okay. So if a solid dissolves, we use the term soluble. And if it does not, we use the term insoluble, based on the solubility rules that we learned in the previous chapter. Okay. Now, we have this table here, and the question is, will these solutes dissolve in these solvents? All right. So the three solvents that we have are in the first column. And so we have ammonia. Oh, let me change the color here. Ammonia, which hopefully by now we have learned that ammonia is very polar. Okay, it's a polar species. This other material, which consists of nothing but carbon and hydrogen, is a hydrocarbon. Okay, and being a hydrocarbon should tell us that this is a very non-polar species. And then we got bromine that is diatomic, and we also learned in the previous chapter that all diatomics, and previous numerous chapters, all diatomics are nonpolar. And so we have two nonpolar solvents and a polar solvent, okay? And then we're going to test these solutes on the other side. So before we do anything, what we need to do is to first define the solute as to being polar versus nonpolar. HCl, hydrochloric acid, or hydrogen chloride, okay? We learned that earlier, that is very polar. We have two atoms that are dissimilar. Automatically, the electronegativity of one of the atoms is much different. That in itself tells you, I got a polar species here. Okay. We have iodine. Iodine again is diatomic, so we have a nonpolar solute. Then we have PCl3, which when we did the Lewis dot structure for that is very similar with respect to ammonia and H3. Okay, and it ends up with a lone pair on the central atom, which automatically should tell you polar species. Okay, because that lone pair is sitting in the middle in the central atom. Then the last one is methane, which is again nothing but a hydrocarbon, which is then now we know nonpolar. So now that we define the solvent and the solutes with respect to polarity, now we can answer the questions whether they're going to mix or not, okay, with each other. Okay, so this is what we just did, define the polarity. So we have the first one, which is ammonia and HCl, which are both polar. That tells you, yes, it will dissolve, okay? Then we have iodide, which is nonpolar, and ammonia, they're not going to mix. There'll be no mixture going on. Then we have the phosphorus trichloride, which is polar, and ammonia, which is polar. So yes, they will dissolve. And then we get a no for methane, okay, based on solubility. Okay. The next solve, the C12H26, which is a hydrocarbon, we end up with a no for HCl because the difference is in polarity. Yes for iodine because of similar polarity. No for PCl3, again because of polarity. And yes for ammonia, not ammonia, methane, again because they both have the same polarity. Keep it in mind, like dissolves like, okay? And then we have Br2, which is nonpolar, and HCl, which is polar, do not mix very well, okay? And then we have iodine and bromine. Yes, there will be solubility there. No for PCl3, and yes for methane, CH4, okay? And so first of all, to be able to answer these type of questions, we have to define the polarity of the solute in the solvent. Once we define the polarity, okay, then keep in mind, like dissolves like, polar dissolves polar, nonpolar dissolves nonpolar, okay? Another analogy that I find here that you may be familiar with, some of you, is the makeup, okay? There's makeup out there that's extremely nonpolar, okay, meaning that you could be hit by a hurricane and all that water and your makeup still hangs on, okay? Because of the polarity. The water is polar, the makeup is nonpolar in character, and therefore water won't allow it to run. And I'm sure there's makeup out there that's not the case, that even tears and little water causes it to run. But it's because our tears are water-based, and if that makeup has any water-based material, it will cause it to run, okay? All right, also, if you've ever worked on cars and you're trying to clean your hands, it's pretty tough just to deal with soap itself. You really got to get some real non-polar material out there to really scrub it up to get that grease off your hands. All right, so when we talk about the terms miscible, immiscible, soluble, insoluble, okay. Miscible and miscible deal with liquids. Soluble, insoluble deal with solids and liquids. So liquid and liquid for miscible and miscible, solid and liquid for soluble or insoluble. Now, the first one, obviously, because we have both of them are polar, they are miscible. And we use the term miscible because we're talking about liquids. Immiscible when we're talking about a nonpolar solvent and a polar liquid. Okay. Immiscible, nonpolar liquid, polar solvent. Okay. Miscible when we have a nonpolar liquid and a nonpolar solvent. Soluble when we have a polar solid and a polar solvent. Okay. We're dealing with solids and liquids. And insoluble when it's a polar solid and a nonpolar solvent. Good example would be this. If you ever take a little butter, put it on the pan to cook something up, throw some salt in that pan. That salt would just remain there because the butter is very nonpolar. Okay, it will not dissolve or cause the sodium chloride to dissolve. But if you're boiling water and you throw some salt in there, it goes into solution, right? Because of the solubility of sodium chloride, which all ionic compounds are polar by nature. It's just that the solubility depends on the compound, whether it's soluble or insoluble. All right, so nonpolar solvent, solid, and polar solvent, we have an insoluble system. Soluble when both are nonpolar, okay? And ionic compound, well, that depends. If we were talking about water, then we got to check the solubility rules, okay? And then insoluble if it's a nonpolar solvent. All right, so the dissolving process, we had talked about how water, one of the properties of water being very polar. And when it dissolves ions, it will, because of the partial positive, the dipole of water, it will solvate the ions. So in this example here, we see similar picture last chapter, I believe, yeah, where you got the sodium ion, and this could be sodium chloride, for example, and the oxygen solvate the sodium ion, where on the other side, we have the chloride negative charge, and those are being adhered to by the partial positive side of the water molecule, okay? Remember, we talked about the ion dipole force. That's what we're talking about here. All right, any questions about polarity? Any questions about soluble, insoluble, miscible, immiscible? Just keep in mind, like dissolves like. Which brings us to concentration and how we define concentration. Well, there are two types of concentration units, I should say, okay? One is the mass percent, okay, which is a ratio of solute over the solvent. It's a weight-to-weight ratio times 100, so it gives you a percentage, okay? Then the other is called molarity. Now, remember way back when, a few chapters back, we talked about moles, okay? Remember how we calculated moles? We started off with X grams of any chemical. We needed the molar mass of that chemical. We divided by the molar mass, and they gave us moles. So molarity is a concentration unit, but it's a ratio of moles of the material, the solute, divided by the volume of the solvent, okay? And we're going to learn how to do both. Mass percent. A lot of the alcohols that you buy out there, like beer, you're like 5%, 7% alcohol, or even the wines, they are percentage alcohol. That's what they're dealing with, is a weight. Occasionally, you may see a weight volume or volume ratio, okay? But it's just simply a ratio. Right, so how do we determine the mass percent? Okay, by definition, the mass percent is defined as follows. It is the mass of the solute divided by the mass of the solution times 100, okay? And that gives us the mass percent, all right? Now, the mass of the solution is not just the solvent, it is the solvent plus the solute. Okay, so that is what mass of solutions define. So whatever mass of solute we use and whatever mass of solvent, we add those together. So now we got the mass of the solute divided by the mass of solution times 100. Okay. For example, if you calculate the mass percent, if you take 15 grams of potassium nitrate, notice here they give you the formula of potassium nitrate, but they want the mass percent. So we don't need to calculate moles. We don't need to calculate formula weight or molecular mass or anything of the sort. All we know is we have the weight of how much potassium nitrate is used, and then it is dissolved in 130 grams of water. So to calculate the mass percent, we take 135 plus 15 because that's the solute, 15 grams, that's the solvent, okay? Then we take 15 divided by the sum of those two numbers times 100, and it turns out to be a 10% solution. Some of you who may be, in the nursing field, or you maybe use a saline solution. A saline solution, which is nothing more than sodium chloride, is a 0.09%. 0.09%. So next time you hear about an IV of a saline solution, that is the optimum concentration, salt concentration for a aqueous system injected into your body, because if it's too much, it can cause damage to your cells. You can one or two things can happen. It can either suck the cells up completely or it can blow them up. So the saline solution has to be just the right amount of salt, because there's a whole new process that's going in, osmotic pressure and so forth, we're not talking about that in this class, but it's very specific, 0.09% sodium chloride for a saline solution. All right, so that's how we calculate mass percent. Now, here, occasionally notice here that in this example, we were given the quantity of water, okay? So we can do the mass percent calculation. There are at times, however, that you do know the solute amount, but you don't know how much solvent you have, okay? Oh, or one or two things. Let me reword this a little bit differently. Okay. This part, the amount of water may not be known, but what you do know is the mass percent that you want, and you know the amount of solute. And so what you are trying now to determine is, given the mass percent that I'm striving for, given that I have X amount of solute, how much water do I need to get me to that percentage that I need to get to, okay? And that's what this next one is doing. It's saying here, how many grams of water are needed to make a 5% saline solution with 10 grams of salt, okay? And we're not concerned about which salt that is. It could be any salt. So we're trying to figure out how much water do I need if I start off with 10 grams of a salt and I need to get to a 5% solution, how much water do I need, okay? And so I set the problem up, okay, as follows. And so 5% is what I'm striving for. I'm told that I'm given 10 grams of salt. So 10 grams, is the solute. So, and I don't know how much water. This is where the water would be. So I end up with this algebraic equation. Now, if I knew the water amount, I can do the math and multiply by 100 to give me the percentage, okay? That's how you normally would, but we don't know what the water is. So we have set up this algebraic expression that looks a little bit complicated. And I'm here to tell you that it's a lot simpler than it looks, okay? And the thing about algebra problems is that sometimes there's 2 or 3 ways to solve for a variable, and not one way is correct. The way that is correct is that whichever way you go to get your answer, that is the correct answer. Okay. All right. So there's the textbook uses the following to solve for x. Okay. All right. So what they did was they took the quantity up here, 10.0 plus x, okay, and they multiply both sides of that equation by that quantity. Well, look what happens when you do that. That cancels out, and you move the 10 plus x over to the left side of the equation right here. Okay, so now I got 10 times 100. So now at this point you can do multiple things. You can, I got two quantities, so I can go multiply these out, and spread it out. You multiply these two and get a number there. That's one way of doing it. Okay. Or you can do the following. What they did is went ahead and multiplied the 10 times 100 to give you 1,000. Okay. Then they got rid of the 5 on the left-hand side. We divide by 5 both sides of the equation. Okay. So that cancels out, giving you 10 plus x, and that's 1,000 divided by 5. Okay. So that is 200. So we got 10 plus x equals 200. Now you solve for x. So you subtract negative 10 on both sides. Okay. Let me do this. Negative 10 on both sides. Luminous 200 minus 10, which is 190. Okay. But given the sig figs that we had to begin with, okay, this is an exact number here, 100. This is a measurement. This is a measurement. These have 3 sig figs. Okay. So there's this one here. So our answer should have 3 sig figs. And obviously we can't write it as 3 sig figs. So when in doubt, what you do is you convert it to scientific notation. Okay. And that is 1.90 times 10 to the second power. So how do we know that answer is correct? Well, we simply take our answer here and we dump it back into the original equation. As you do the math, you should end up with 5.00 equals 5.00. And if you don't, that means that your algebra was incorrect, and go back and check your algebra, okay? Because 5.00 equals 5.00, that is a true statement, okay? That is correct. 5 equals 5. So we just check it. Sorry about that. I'm having to sneeze so much. All right. Let me clear this up. All right. So that is the mass percent. So one or two ways we can be given the solute and solvent quantity like we did here. Okay, and you simply plug in the numbers in that equation. Remember that the denominator is the mass of the solution, which is the mass of the solvent plus the mass of the solute. Okay, don't forget that, because you end up with a different percentage. Specifically, if you forgot to do this part, you end up with 11.1%, which is incorrect, okay? So don't forget to add. That's all you. Which brings it, and then of course the other way is you don't know how much water you need, so but you're given the amount of solute. So you calculate and solve for the algebraic equation, solve the algebraic expression for X, which is the amount of quantity of water that you need. Okay. All right. Now, which brings us to molarity. By definition, is the units are moles per liter. Okay. So right away, you know, if I have grams, I need the molar mass to determine the number of moles. And the volume could be given to me in liters, which is great, or it could be given to me in milliliters or in kiloliters or centiliters. It can be any of the others prefixes, okay? And you need to be able to remember how to convert those into liters, okay? Either kiloliters, centimeters, milliliters, convert those into liters. So you have the units of moles over liters. All right, so let's take this problem here. It says calculate the molarity of 9.99 grams of potassium bromide. Okay. If you take 9.99 grams of potassium bromide and you dissolve it in water and you actually put it in a special container that has a known volume, exact volume, that we bring the water up to that level. And we call those volumetric flasks. And normally we don't use 2.5. We generally have even numbers like 1 liter, 2 liter, 3 liter, even 5 liters. But we're going to go with the flow here. And we're going to dissolve it to exactly 2.5 liters. Okay. What is the molarity? Well, step number one, we need to calculate the moles. Okay. And so we need the molar mass of potassium bromide, which is 119.00 grams. And you forgot how to do that, go back to the flow chart we talked about, where we did the calculations. And that flow chart tells you, okay, here, I'm starting with grams given. I need to calculate how many moles, okay? And so 9.99 divided by 119.00 is equal to 0.08395 moles of potassium bromide, okay? We are given the volume of 2.50. I wouldn't, don't truncate anything. You know that you got 3 sig figs to begin with at 9.99, and you have 3 sig figs in volume, 2.50. So your answer must be left with 3 sig figs. And so that is 0.0336 moles per liter, all right? So in essence, if I take out 9.99 grams of potassium bromide and I dissolve it up to exactly 2.5 liters of water to make 2.5 liters of solution, the molarity of that solution is equal to 0.0336 moles per liter, okay? Moles per liter. All right, so there are questions in your ORE or ER textbook, and there are the practice worksheets. So knock those out, go through them. In fact, if you don't quite see them, see how it's done. Those are perfect types of questions you can bring in, you know, Thursday for the next 3 Thursdays, I should say. Okay. All right, let's try another one. Here, we need to calculate the molarity if we take 5.0 grams of sodium phosphate, okay? and is dissolved in water, and it made 255 milliliters of solution. Well, before we start, we need to write the formula, okay, for sodium phosphate. And so going back to how we were putting these together, we got the phosphate ion, and we know from the polyatomic ion table that that is the formula for that polyatomic ion, PO4 -3, okay? And we know that sodium is a group 1 metal, so therefore, when it becomes ionic, it will have a +1 charge. So that means that we need 3 sodiums for every phosphate ion. So our formula becomes Na3PO4, okay? Once we know this, we have 3 sodiums, 1 phosphorus, 4 oxygens, okay? Plug in the atomic weights for each one of the atoms, tally it up, and that gives you the molar mass, because we need the molar mass because we're starting with grams of sodium phosphate and we need to get to moles of sodium phosphate. The volume is 255 milliliters, so we are in units of milliliters. So we need to convert that to liters. So we know that there are 1,000 milliliters in 1 liter. So that's our conversion factor to convert the 255 milliliters into liters. Or you can recognize that I just moved the decimal point over 3 positions. That's one way. But if you're not that confident with that yet, you have this. Always will have that. So that's the information they need. And the first information is that when I added all that up, 3 sodiums, phosphorus, 4 oxygens, it has a molar mass of 163.94 grams, okay? And so that 5.0 grams corresponds to 0.03049896. I keep all the numbers, don't truncate anything until you're done with the math, okay? Now, keep in mind, you got 2 sig figs right here and 3 sig figs right here. Remember, we don't use the atomic weights or the molar mass for determining sig figs, nor do we use the conversion, the exact numbers, okay? So, but these are measurements, 5.0 grams and 255 milliliters are measurements. So our answer should have no more than 2 sig figs because we are dividing, okay, the moles over liters. So we should have 2 sig figs, but keep all your digits until you're done with the end of the calculation. And then truncate accordingly. We know that in 1 liter, there's 1,000 milliliters. So that converts, this one converts the 255 milliliters into liters, which is 0.255, okay? So now we plug in the numbers and we end up with 0.12 moles per liter, okay, with 2 sig figs. So if you take out 5 grams of sodium phosphate and then you dissolve it to 255 milliliters, okay, you have a molarity of 0.12 moles per liter. All right, well, ladies and gentlemen, no, oh, no, I didn't see who else is here. All right, well, this brings us to the end of chapter 15. Congratulations, you survived 15 chapters of chemistry. All right, don't forget the assignments. I went in there, and don't forget you have a few assignments that are coming up. Some of you did not complete the last activity. If I'll give you the benefit of doubt, given the holidays and all that. If the last activity wasn't completed, go back and do it. Let me know when you fill it in, and I'll take off the penalty, the late penalty for the last activity. It's, I believe, activity 14. I think only about 2 or 3 people had done it. Okay, so since you showed up here, I'll take off that penalty if you get it not turned in. Let me see what else. I can't think of anything else. There's a practice final exam on the course website, which gives you an idea of the type of questions that are asked. Thursday, next Tuesday, and the following Thursday, I'll be here. If you need any help or assistance, get ready, come in with questions. I mean, we can go over them. If not, finish your assignments and knock out that final, that exam number 5 and that final. And it's been a pleasure. So take care if I don't see you again. All right. All right. Any questions?